The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today, what we want to do is talk about something at a much higher scale than what we've thought about through most of this semester. And that's partly by design in the sense that over the course of the semester, we started with kind of enzyme kinetics or molecular binding kind of events, and we slowly built our way up to larger and larger scales. Now, there's always this question about whether we're claiming that we really understand how the higher levels of organization kind of result from the lower level interactions. And I'd say we definitely don't understand all of it, so you shouldn't come away with that as the notion. But at least one thing that I think is fascinating about this area of systems biology is that much of the framework that we use to understand, say, molecular scale interactions or stochastic gene expression, so these dynamics at the smaller scale, much of those ideas and such certainly transport up to these higher scales or translate up to the higher scales where, in this case, we're using kind of master equation type formalisms to try to understand relative species abundance. And so I think part of what I like about this, this topic of neutral theory versus niche theory and so forth in ecology is that you can just see how very, very similar ideas that we applied for studying stochastic gene expression can also be used to try to understand why it is that some species are more common than others when you go and you count them, in this case, on an island in Panama. Okay. Now, the subject is by its nature less experimentally focused than much of what we've done over the course of the semester, and that this is really a topic that tends to be a combination of mathematical theory with kind of careful counting of species in some different areas and trying to understand what that means. But I think it's an area that there have been a number of physicists involved in over the last 10 years, and I think that it's fascinating because it does get to the heart of what we are looking for from a theory, what kind of evidence do we use to support a theory or to refute it, and I think it's so I think there are a lot of kind of very basic issues kind of about science that come up when we start thinking about this question of neutral theory in ecology. And since it's a totally, for many of us, a totally new area that we don't know very much about, you can come to it with maybe fresh eyes, and you don't have the same preconceptions that you would have for many other models that you might be more familiar with in the context of molecular cell biology. Okay. Right, so the basic question that we're going to try to talk about today is just the question of why is it that when you look out at the world, you see that there are some species that seem to be abundant and some that seem to be rare. Right? What is and are there patterns that are somehow universal, and what kind of sort of lower scale processes might lead to the patterns that we observe? Okay. And I think that this paper that we read is, I mean, it's not that it's well, can somebody say what the actual contribution, the scientific contribution of this paper was? Yes. They did a calculation, right? But it's a little bit more specific than that. What is it?
They came up with the closed form equation.
That's right. So they basically there was a model, this neutral theory in ecology that we're going to explain or try to understand. You can simulate the model, but then there are possible issues associated with convergence or something of those. Although it's hard to believe that that's really such a concern, right? But you can simulate that model. What they did is they just showed that you could get an analytic-y kind of expression for it. It's not a super analytic expression, but at least it's not a straight-up simulation, right? You kind of numerically do something, integrate something as compared to doing the stochastic simulation. So it's not that that's. Yeah, so it's not that in and of itself is what you feel like it's not what we necessarily care so much about, but I think that it still is just a nice short description of the model and of the assumptions that go into it, and you get a little bit of a window into the debate that's going on between these two communities of the kind of the neutral theory guys and the niche theory community. Okay. All right, now I want to, right, so there's only one figure in this paper. And it's an example of the kind of data that we want to try to understand, right? So there's a particular pattern in terms of the relative species abundance, and we want to understand what kind of models might lead to that observed pattern. Okay, but given that there's just one figure in the paper, we have to make sure that we understand exactly what is being plotted. And what I've found from experience, and actually even the answer to the email question that was sent out, I think was incorrect on one of these things. So we'll talk about that some more. So beware. We'll figure it out. But I think it's actually surprisingly tricky to understand what this figure is saying. Okay. But first of all, can somebody describe what not what the figure is saying, but just what the data is supposed to be? And yeah. Where do they get the data? Anything that's useful. All right, there's an island. It's called BCI, or Barrow, Colorado Island. Okay, yeah, so it's a 50-hectare plot. Okay, 50 hectare. Does anybody know what hectare is? Hectare? Yeah, it's a lot more than a square meter. Yes, indeed. Yeah, I guess is this an English unit of measure? This is the kind of thing that I have to Google, but it's 1 hectare is equal to 10 to the 4 meters squared. Okay. All right, it's a good thing to memorize. Right, so it's
exactly or approximately?
I think it's an exact. I think it's an exact. Right. Yeah. Yeah. So apparently it is a metric. Right. So the idea is that this, if you take 100 meters by 100 meters, this is a hectare, and there's 50 of them. Right. So if you come out, it's about like a half a square kilometer, to give you a sense of what we're talking about. Okay. And what do they do on this plot? All right. Okay, yeah, and how do they decide which trees to count? Do they count every tree that? No,
just the ones that form the top layer.
Right. I think that the way that they decide. Okay, yeah. Okay, so they count. Yeah. Does anybody remember how many trees were counted? Right. So there were 21,457 trees. 21,000 trees in this 50-hectare plot, and they assign them they identify the species for each one of these 21,000 trees, and they assign them, and they found there were 225 distinct species. Right, so this is really quite an amazing data set. Okay? Because I can tell you that I would not be able to do this. Okay? Right, they have. This is highly skilled biologists that can distinguish 225. If they can identify these 225, that means they have to be able to identify other ones as well, right? And they did it for 20,000 trees. And indeed, Barrow, Colorado Island is one of the major Smithsonian research institutes where they've been tracking. They do this like every 5 years or so, where they do a census where they count all of the trees, and they're also tracking many other, it's not just trees, right? They're doing everything there.
These are only plants.
What's that?
These are only plants.
No, I think they do. I think so I visited BCI, and it seemed like they were studying all sorts of things. I mean, there were nice looking birds there.
No,
Once again,
in this census.
Oh, in this census, it's only trees, and the way that they decide. All right, so the way that they decide which the trees to do, it's the ones that are more than 10 centimeters dBH. Anybody can guess what dBH might mean? It's actually diameter at breast height. Okay. Diameter, breast height. So what they do is they walk up to the tree with a ruler, and then if it's larger than 10 centimeters, then they count it. Okay? And you need to have some threshold at the lower end, otherwise you're in trouble, right? And there were plenty of trees that satisfied this requirement, right? Okay. Now, then what they do is they have, for all these trees, it's assigned to some species. Okay? Now, we want to know what the basic goal of this branch of biology or ecology is to try to understand where the pattern from this sort of data, where it comes from. Or first describe it, and then once you have a description of it, then you can try to understand what microscale processes might lead to the pattern. And the pattern is what's plotted in figure 1. It's the only figure in the paper. I have reconstructed a rough version of it here for you on the board. But if you want a more accurate version, you can look at your paper. Okay. Now, we want to make sure that we understand what the figure is saying. So we will ask the following question. What is the most common number of individuals for a species in this data set? Okay, most common / frequent, right? Number of individuals for a species to have, for a species in this data set. Okay. Now, it's maybe worth just saying something a little bit more, right? So you notice that they were not trying to count the total number of species altogether. This is, and in general, all of this field of relative species abundance to try to understand them. What you do is you typically take one trophic level, right? So some of the classic studies were of beetles in the Thames River, right? So you take some, the idea is that it's some set of species that you think are going to be interacting, maybe competing with each other in some way, in the sense that they're maybe eating related things and being eaten by related things, right? And so in this case, this is, these are the trees on Barrow Cholera Island, and you can imagine that this is useful, right? In the sense that the fact that it's trees instead of something else means that you can actually track the individuals over time. And when you go to the island, what you see is that all the trees have, they're wrapped by something tagged, and presumably they have some system to tell you which species that is, so that they keep records of everything, right? But question is, what's the most common number of individuals for a species in the data set? Do you understand what I'm trying to ask? And we're going to do approximate, so we'll say 1. Or this can't determine. We want to know what is the mode of this distribution of the number of individuals for each of these species. Do you understand the question? All right, I'm going to give you 20 seconds to look at this. All right. Oh, we don't have our. The TA always lets me down. All right, yeah. So, all right, yeah. So you can do A, B, C, D, E. All right, are we ready? Okay, it might be. Or yeah, and you can just do this if you. But given this was the only figure in the paper, and that this is a basic property of the distribution, I'm sure that you figured that out last night, anyways, right? Especially since it was one of the questions in the pre-reading. So you presumably already thought about this question, right? Okay. Yes? Yes. Yeah. All right. Ready? 3, 2, 1. All right. So we got, I'd say we got a lot of B's. Okay. So it seems like B is the most. All right. All right. So this we'll put a question mark here. All right. And what? right, can somebody verbally say why their neighbor said it was that the mode of the distribution is around 30? Yeah. The tallest bar there is around 30. OK, that's a very practical definition, right? So that's normally what we mean by the mode, right? There's a slight problem in all this, which is that this thing is plotted in a very kind of funny way, right? So if you look at the figure, what you'll see is this number of individuals, and down here it says log 2 scale. Okay. Right. Now, when we say the mode, what we're wondering about is that, if you just take the most typical kind of species of tree that's there, how many individuals do we think there should be there, right? And not, okay, well, of course, the typical is hard to define, right? We can talk about mode, median, mean, et cetera, right? But the most common number of individuals for a species as a data set ends up not being 30, right? It ends up being 1. Okay. And we will try to reconstruct this right now, okay? Because you have to do a little bit of digging to figure out what is being plotted here. But it's not the raw data. The problem here is that this is on this log scale where the bins here are growing kind of geometrically or exponential, whatever, as you move to the right. Okay. So over here, this thing only contains one real bin. And actually, we're about to find it's half a bin, which is even weirder. Whereas out here, this is maybe 30 bins. So the number of species that we're going to put in this bin is everything between, I don't know, it's going to be around from 20 something up to 50 or so, right? So the number of kind of true bins that end up in each of these plotted bins is going to grow geometrically as we move to the right. Okay, so this is a very funny transform of the data. Okay, and indeed, I think it's always nice to just in life, you always plot the raw data first, and then what you can do is you can do funny. I mean, there's a reason to plot it this way, right? Because this is where they get this idea that this might be described as a log normal, right? The idea is that if you take a log of the data, then you get something that looks like a normal, right? But you always plot the raw data first. Okay. All right. So let's try to figure out what the raw data look like. Okay. And now what we're going to do is we're going to have real scalings, honest to goodness numbers. Okay. So this is going to be now the number of species again still. Right, so this is asking how many different species do we see with 1 member or with 2 members or with 3, 4, et cetera, right? And I don't know how far we're actually going to be able to get. But in this one figure in our paper, they tell us what the histogram means. Right? So the first histogram bar represents what they call phi1 divided by 2. Right? Phi1 was the number of species observed with 1 member. Right? Which means that even this first plot bar is not the number of species observed with a single individual. It's half of that. Okay? I mean, you can argue about the consistency of how these things should be, but that's what this thing is plotted, right? So, and it looks like it was 9 here, so this should be 18. Okay? So I'm going to put up here, here's a 20, and here's a 10. All right, so here's an 18. Okay. Now, what did they say? In this bin represents phi1 divided by 2 plus phi2 divided by 2. Right? So they took the number of species where they saw just a single individual plus the number of species where they saw 2 individuals, and they added those, and they divided by 2. That's this number. Okay? All right, we're not going to go through this whole process because it's a little bit tiresome, but I will. I've already done it for you. Okay? So I'm going to plot a few of the things to get you there. Right, so I calculated it was 19, 13, 9, 6. Okay, it becomes ill-determined once you get out here. Okay, in the sense that we don't have enough. It's not uniquely specified going from that to that, as it has to be, right? But I calculated it's around 5 in here for a few, and somewhere in here it's going to go into 4. And then this might go down to 3. Okay, and then da-da-da. Okay. Now, if you look at this and the rapid fall off, right? How do you think that you're going to find any species that have more than 20 individuals? Right? Okay, we're going to vote. Okay, so you see this falling off? All right, so let's say that I just showed you this and I haven't yet calculated the rest. All right, do we think that there's going to be any species with more than 20 individuals? Okay. All right, greater than 20 individuals, question mark. We have, all right, 1 is yes, 2 is no. All right, it's going to be yes, no. All right, ready? 3, 2, 1. All right, so we got some 2s. All right, so I'd say that most people are saying no. There's not. Look at this, fall off. There are not going to be any species with more than 20 individuals. Okay. Although we already know that there are many species with more than 20 individuals. I mean, this plot is useful for something, right? That you can see that there are, and we know exactly the number of species that have more than 20 individuals, roughly, right? So okay, those ones are all in these. So you can see that there are hundreds of species with more than 20 individuals, right? And indeed, it looks like there were 2 or 3 species that had like more than 1,000 individuals, or 1,500, or whatever the cutoff there was. Right? Okay. So this distribution starts out, rather high, but then falls quickly. And out here, it's going to be very, very sparse. Right? So there's going to be a bunch of numbers in here where there's not any species in the histogram, but then out there's going to be one, right? And indeed, you have to go really far out, because there's one species out there that has a couple thousand, right? And indeed, the mean number of the mean number of individuals per species has to be around 100, right? We know how to calculate a mean. This divided by this is just short of 100. Right? So the mean number of individuals in the species is around 100. The mode is 1. And the median all right, well, okay, ready? We said that we decided this was the mode. Okay, where's the median going to be? Is it going to be A, B, C, D? Ready? 3, 2, 1. All right. Yeah, indeed, this tells you pretty clearly where the median is. The median, this thing is indeed around the median, right? Because you can say, oh, it's about the same numbers either side, right? So the median is around here. All right, and I told you where the mean was again. Do you guys remember where? All right, ready? 3, 2, 1. Mean. Oh no. Okay, mean. All right. Okay. So this is a very, very funny distribution. I guess I want to highlight. Okay. And I think it's not at all what you would have expected somehow. Right? At least if you had described this measurement process to me, if you told me that you went to this island and you counted 20,000 trees, okay, I don't know how many species I would have guessed, but okay, you're 220, that's reasonable, right? But I would have guessed that, I would have guessed it would have looked something like this on a linear scale, maybe, right? That it would be, that there would be a bunch of them around 50 to 100, and some of them go a couple hundred, some of them, right? So I guess I would have thought that, that the mean, mode, median would all be kind of a more similar thing, right? But this is just not the way the world is. Okay? It's not just on BCI. Right? People have been, for hundreds of years, have been studying these distributions. And things that look like this, with extremely long tails, this is what people see. Okay? Now you can argue about exactly how fast it falls off and whether it's different on a mainland or an island. But this basic feature that rarity, or that rare species are common, this seems to be just, that's what you always see. Okay? All right, so this is the thing that you have to remember. Rare species common. And I think that this is the basic surprising thing in this whole field. And the ironic thing is that even after spending all this time reading about theories to describe these distributions, it's still very possible, and I would say based on the statistics this year and past years, it's not just possible, but it is the standard outcome is that after reading this paper, you do not realize that the distribution looks like this, right? You somehow still think that it looks, you kind of still think this is like a linear scale, where the typical species, right, has this, where the mean, median, mode are all about the same thing, right? So, so I guess always plot the raw data in an untransformed way. There are theoretical reasons why it might be nice to plot it like this, but be very careful about what you're doing, because then you're left with a mental image of a histogram that looks like this, and that's very, very dangerous. Yeah.
But why is it not a sensible way, like what? It's okay to aggregate data like in bins like that, and I mean, sure, like exactly one species is the mode, but like, do you really want the?
Yeah, no, I understand what you're saying. That it maybe, I guess it's just that there's a qualitative aspect to the data, which is that most species are very rare. And this is something that I think is surprising. I think it's deep. And it's something that you do not realize.
Most species have more than, 16. I mean, it depends what you mean by rare, but like,
Yeah.
the weight of the distribution is away from 10.
That's a good point. The species density is clustered around the low numbers.
Right.
But actually, most species have more than 30.
OK, well, we can pick. I mean, maybe the surprising thing is that just if you take, the mean is 100, right? And so I would have thought, and that if you plot number of species as a function of the number of individuals, right? Number of species, right? That if given those numbers, I would have guessed, OK, here's 100. I would have guessed, here's 50. So just to highlight that this is a 150. So linear scale, I would have, guessed it looks something like that. Maybe larger than root n or something. But
What would that look like in a log scale? It would look like if it's like the log of the counter. It's like, so it goes up really fast. And then
right. So this thing would be kind of like, it would all be. All the weight would be in. It'd be like all here plus a little bit on each of these, right?
Yeah, but it's not. I don't think it's actually that different from. Like the only thing that's different is the tail on the left, which is that.
And the tail on the right.
Yeah, it's a little bit longer.
Oh, no, it's a lot longer, right? Because this thing, all of the weight is between 50 and 150, right? Which means that all of the counts are basically going to be, well, all the counts are going to be it's these two, basically. Because this thing comes out either way. So in this case, if you take that histogram, put it on this kind of scale, you end up with 2 bars up high, nothing outside. Right? So that's a very different distribution. And it's not to say that this is a ridiculous thing to do. It's just that the problem is that your mental image of what the distribution looks like ends up being incorrect, in the sense that you have a qualitatively different sense of what's going on, right? And and it's really, if you go up to 10 species here, right? And 10 is way down here, so you'd think there should be that no. If this is your mental, if this is what it looked like, there would be essentially no species with fewer than 10 individuals, right? But if you come over here and you add it up, right? You take, it's like mean of say 6 times 10, 60 out of 200. So this is, a quarter or a third of the species on this plot of land have fewer than 10 individuals, right? And 10 is really a very small number. It's just a question of, well, rare species are common. I guess I think that this is I think it's a true description of the observed distribution here and elsewhere, and it's not something that you appreciate or realize when you plot it in that way.
But you can get this information from that plot. I mean,
No, I agree. You can get it, but it was only 10% of the group got it, right? The fact that you can get it, I mean, right? Yeah, no, it's possible, but you don't get it. That's a practical statement. Yeah, I'm not dead set against this distribution. It's just that it makes everybody think something that's not true, right? So if you think that that's okay, then I can't help you. No. I mean, it's just it's fine. I mean, it's okay, but it's just you have to be careful. Is my only statement. Yeah, and I very much want you to take away, at least because I think this is an accurate description of the data, is that rare species are common. And as one of the readings, I think it was in this paper, or maybe it was a different one that I was reading. Even Darwin, when talking about this, he commented on this fact that rarity of species is somehow a typical event. Right?
Common species are rare.
And common species are rare. That's right. Right. It's just that this distribution is hugely skewed. Right. Okay. Okay. So this is the these are the measurements, and this is kind of you can look at them. I think it's good to look at them in both of these ways because you can't even plot the data on a linear scale, right? So that's a good reason for doing it, but I think it's good to have both of these pictures in mind. Okay. Okay. All right, what we want to do is talk about two classes of models that give something that's essentially this log normal distribution. Right? So on a log scale, it looks normally distributed, approximately. Okay. And those two models are going to be kind of a niche-based model and a neutral model. All right. Can somebody in words explain what they maybe see as the difference between this niche and the neutral kind of approach? Yeah. Well, maybe. All right, every species is in which one? All right, in the niche theory, the species are different. All right? So this is it seems like a ridiculous statement, right? That, I mean, do you believe that species are different? All right, we can vote, yes or no. Ready? 3, 2, 1. Yeah, well, okay, well, somebody's been convinced by the neutral theory. All right. Yeah, so, it's clear that species are different. And the question is, which patterns in the data do you need to invoke differences in order to explain? Right? And I think that one maybe theme that's come out of this relative species abundance literature and the debates between the neutral and the niche guys is just that this distribution is less informative of the microscale or individual kind of interactions. It's less informative of those interactions than you might have thought. Okay? Because multiple models can, I think, adequately explain such a pattern. And in all areas, we have to remember that you make an observation and you write down a model that explains that observation, right? So what you do is you write down a model, and writing down a model, what that means is that you make some set of assumptions, and then you look to see what happens in that model. And if the model is consistent with the data, that's good. But it doesn't prove that the assumptions that went into the model are correct. And this is a trivial statement. I've said it before, but you have to. It's like you have to tell yourself this, or remind yourself of this, kind of once a month, okay? Because it's just such an easy thing to forget about. Okay. All right. Now, the niche models indeed assume that the species are different, and that's reasonable because we think it's true. But then, of course, there are many different ways of capturing those differences, and then you have to decide whether the assumptions there are reasonable or whether they're necessary, essential. We're going to, in the context of the niche models, we're going to think about the so-called broken stick models. But even more concretely, all right, so basically, you get log normal distributions when there's some sort of multiplicative type random process that's being added together. Okay, so you get you get normal distributions when you have sums of random things going together, right? This is the central limit theorem. But when you have multiplicative kind of errors or random processes come together, you get log normal distributions. And I want to highlight that that does not necessarily have to tell you so much about the biology of it, right? Because a classic situation where you get log normal distributions is if you take a stone and you crush it. Okay, you can do this experiment at home, and then you measure the mass distribution of the resulting fragments. Right? The distribution of mass is log normal. Okay. All right, so just take a stone, grind it under your boot or hammer it, and do this, just kind of rub it right in. Okay, you'll get some distribution of fragments. You can go for each of the fragments, measure the mass, and indeed you end up getting a log normal distribution, right? Because there's some sense that what's happening is that you take a larger mass, you break it up randomly, and then the resulting fragments, at some rate, each of them you break up randomly. And the small ones are maybe kind of as likely to get broken up as the big ones, so then the small ones can still get even smaller. So you get, but then there's going to be at some rate some very large ones. Okay? So such a process ends up, it's not biology. Okay? This is just something about the nature of the breaking up of this physical object. And indeed, the basic idea behind many of the niche models that give you a log normal distribution is equivalent to crushing a stone and measuring the resulting distribution. Okay? And I'll describe what I mean by that. Typically, what the broken stick models have, they say there's some resource axis. Okay, this is a resource axis. And this could be, for example, where you're getting food from. Okay? Now, we're going to have to divide up this resource axis among some number of different species. And what we're going to assume is that the number of individuals in the species is proportional to the length of the resource axis that it's able to capture. Okay? And I want to make sure I find my notes. Right, and this I want to highlight, this comes from MacArthur's, this is MacArthur in the 1950s. MacArthur, this is 1957. Okay. All right, so we imagine there's this homogeneous resource axis. We're going to break it up into n segments, and the abundances are proportional to the length. And the idea is that if this process, if you just break this up randomly, so let's say that you just draw n-1 lines randomly, or n-1 points randomly here, and you ask about, okay, now you have n species with n, so n species with n different abundances. Okay. The question is, does that give a log normal? Okay, so we'll say, we'll say n-1 random points. Do you understand what I mean? So you sample uniformly once, sample uniformly twice. You do that n-1 times, and now you have n. Okay, and then we say, okay, this is the first species has this many individuals, the second has this one, the third has this one, etc. Right. The question is, does random points, does that lead to a log normal? All right. Yes and no. Let's think about this for 10 seconds. n-1 random points, log normal distribution. All right, ready? 3, 2, 1. All right, so I'd say that we have a majority are saying no. Can somebody say why that is? Because it's something else. Okay, that's fair. Okay, but can you say qualitatively why it is that this is not going to work?
You can't have very long gaps.
Right, that it's going to be very unusual that you get a very long gap, What about the other end?
Also very unusual.
Now I'm a little bit worried. I think that that's true, right? All right. Well, I'm going to say that you're not going to get this super long ones, but I think that the distribution of might still be peaked at its short values. No? Random. Because what's true, because if we were just traveling along this resource axis and at a rate that's kind of exponentially distributed, like Poisson rate, we just dropped points. That's something very similar to this random.
Except you're limited in the number.
No, is that not true?
You're sampling from the syntax.
Yeah. All right. All right. Yeah. And I have. Okay. I'm a little bit worried that I might be. Yeah. I'm not 100% confident. Depending on how I look at this, I get different distributions on the. Yeah.
But I think the first thing that you said, where you just say, okay, I'm going to pick n minus 1 points.
Yes.
Is a different thing than going along the axis and exponentially dropping one. Right?
I agree. It's different. Yeah. No.
I don't think that would be the ideal way to simulate it, because you would be very likely to just get this giant thing at the end when you're finished.
What you could do,
Yeah.
you could go along, you could drop n plus 1, or n plus 2 points.
Yeah.
And
No. I
then
think.
rescale so that your 2 endpoints are.
Yeah, and because I think that the probability distribution does grow. Right, I think that I'm going to side with you and say, all right, so we've decided that there are not going to be as many short sticks and there's not going to be as many long sticks as compared to a log normal. Do we agree with that? Okay. All right. So So at least we agree that it's not going to be a log normal, right? So you're not going to get this huge variation of some very long sticks and some very short ones. Okay. Now, the question is, what kind of thing? How would you change this sort of model in order to generate a log normal? And the answer is that what you have to do is you have to have some sort of what is called some niche hierarchy, or some hierarchical breaking. Just like what led to the stone giving a log normal is that you have to have some successive process of breaking things. Okay. So this is what they call some hierarchy model. Right. And the key thing is that it's sequential. Okay. Right. You have your resource axis, and you first you have some rule for breaking it up. It could be that you just sample uniformly or some other probability distribution. But the idea is that you have, and the way that you might think about this is via just everything up on the board is so nice and useful. I feel bad getting rid of it. Okay. This thing is not true, so I don't mind erasing it. All right. So let's imagine some bird community in the forest, and we're going to think about where is it that the birds are getting their grub or their food to eat. Okay. Bird community. All right. So you might first say, okay, well, in this axis, and now the axis is somehow vertical, you could divide them up into the ground foragers as compared to the tree foragers, okay? In terms of where they're getting their food, okay? And and you can say, oh well, how much of the food is on each side? Say, oh well, we'll say 30% on the ground, 70% on the tree, or there's some right. So this is along the stick distribution. You cut the stick in some way, or you break the stick in some way. Okay, but then within the tree foragers, you'd say, oh, okay, well, the resources might be separated, and this is really like speciation. A species, this is the niche. The species are focusing on different niches. Okay, so you'd say, oh, well, some are going to focus on the trunk, some will focus on branches. Okay, and again, this part of the stick is now broken or divided among different resource locations with some amount. But then also, you're going to get speciation in different directions here because there's both the surface. I don't know if you guys have ever eaten grubs, but there's the surface grubs, and then there's also the sub-bark grubs. Okay. Right. And so you kind of do this process multiple times, right, where you kind of pick different branches and you break them to divide up the niche, and then you end up with a log normal type distribution. Right. And this is some similar process to to the crushing of the stone, because the idea is that the stone there's sequential breaks of the stone. So the stone first breaks into, maybe simply 2, or it could be 3. First there's one breaking, and then one of them is broken more. So given this process, you end up getting a log normal distribution. Yeah.
So, but you also have a distribution like for how far, because I guess there are 2 questions. Like when you break your stick, you assume somehow that you uniformly break it.
Yeah. So people have a lot of work has gone into the question of how it is you should break the stick, right? So given that you have this tree foraging stick, and people, so. And in particular, on a practical level, what they do is they ask, well, what probability distribution gives you the best agreement with the data, right? Is it uniform, or is it, it's broken like this, or is it, and in some cases people say, well, it's actually tilted on one side because, if there's some process that, in the context of succession and some other environments, there's an idea that if a species first gets somewhere, they can kind of monopolize a larger fraction of the resources than if it's divided kind of at equally at some beginning, and that's going to affect what this probability distribution is when you break each one. But there's always this question about how well these notions, how constrained are the notions, and so forth. And I'm agnostic on that point.
But you also need a distribution for how many times you break each.
Yeah. Yes. Although it's just that if you do this process, it's like a central limit theorem type result. So you have to do it enough times so that you get to some limiting distribution. And then you could keep on doing it, but then in the end, we always say is that species abundance is proportional to the size, right? So we're going to scale ultimately to get the correct number of individuals. So it's not that, it's just you have to do it some reasonable number of times so that the randomness kind of washes out, and you end up approaching that limiting behavior. Okay? Does that make sense? Okay. And indeed, I just want to mention a major result in this field, in that these niche type models successfully explained or predicted another pattern that had been observed, which is the so-called species area relationships. So this is just saying that, let's say here we looked at 50 hectares and we asked how many species were there, right? 225 species and 50 hectares. Now the question is, if instead of looking at 50 hectares, we instead looked at 500, okay? Do you think that the number of species we observed would have gone up, stay the same, or gone down? Up, same, down. Ready? 3, 2, 1. Up, up. Right? If you look at a larger area, you expect to see more species in a larger area, right? And people really do this, where they look in some area, going from, say, they take a meter and they count all the species, and then they go and here's 100 meters, and they count all the species, and then they ask, okay, how many species do you see as a function of the area? And what people have found is that the number of species you observe is something like, it's proportional to the area to some power, where z is around a quarter. Okay. And of course, the area goes as some r squared. So if you wanted to, you could say it goes as the square root of the radius. I don't know, whatever. But the number of species in some area, it grows, but it grows in a manner that is less than linear. Does that make sense? It definitely makes sense that it's less than linear, right? Because linear would be that you sample a bunch of species here, and then you look at another identical plot, you get some other species, and it would say that you really don't expect any of those species to overlap, right? That would be a weird world, right? So it very much makes sense that this is less than 1. Of course, it didn't have to be this power law, but one thing that has been discovered around the world is that power laws are very interesting, but once again, many different microscopic processes can lead to power laws. The niche models have successfully predicted or explained why it might have the scaling. But it turns out that, that neutral models can also predict it. And it may just be that lots of spatially explicit models will give you some power law type scaling that looks kind of like this, right? So once again, it's a question of how convinced you should be about microscopic processes based on being able to explain some data. And I think it's one thing, the best cure for this danger of assuming that the microscopic assumptions are correct because the model is able to explain something is that if you can find some other very different set of microscopic assumptions that also explain the patterns, then it becomes clear that you have to take everything with a grain of salt. Right? And that's, I think, part of what's been very valuable about this, about the neutral theory contribution to this field. Yep.
Does this just come from, like, if you assume that all the individuals are uniformly distributed and then you look at distribution?
Yeah, so so the cases that I've, so there are multiple derivations of this, so it's a little bit confusing. But there are, well, okay, yeah, so the models that for example, the neutral models that I've seen that lead to these patterns, they basically have the individuals randomly, either with sex or without sex, kind of, diffusing around, and then they divide, and then this, and then you can explicitly just do the different spaces and see that you get a scaling, right? So it seems to be a surprisingly emergent feature of many of these models. So once again, it may be something that tells us less about biology than it does about math or something, right? Any other questions about this kind of the base notion of this niche hierarchy type models? Okay. All right, so I want to spend some time talking about this neutral theory in ecology, just because and the math, in particular the derivation of this particular closed form solution, is not really so interesting or relevant. But I think it's very important to understand what the assumptions are in the model, and maybe also something about the circumstances in which we think that it should apply. Okay. All right, so the basic idea is that we have, what we hope is some meta community that is large, okay? And then we have an island. So this has to do with this theory of island biogeography. All right, we have an island over here, and in the context of the nomenclature of this paper, there's some community size J here. This tells us about the number of individuals. Okay. Okay. And they're distributed across some number of species. Okay. Now, the neutral theory, the key thing is that we assume that all individuals are identical. Once again, and it's not that the neutral theorists believe that this is true. It's that they think that it may be sufficient to explain the patterns that are observed. Okay? Right. And when we say that all individuals are identical, what we mean is that the demographic parameters are the same. Okay? Birth, death rates. Okay? And it's even a stronger assumption in some ways than that it's assuming that the individuals are the same, the species are the same, and there are no interactions within the species as well. So there's none of this, no alley effect or no specific competition. Right? So the birth-death rates are going to be independent of everything, okay? Which is an amazingly parsimonious model. And it's kind of amazing you can get anything out of it, right? All right. And then we have a migration rate M. It's a migration. It's either a rate or a probability, depending how you think about it. Rate or probability M. And can somebody remind us what how we handle that?
We'll have this matrix
Yeah, that's right.
transfer an individual from the meta community to the island.
Okay, perfect.
We do something to the island to make sure that the number of individuals.
Yeah, right. So what we're going to do is we're basically going to pick a random individual here each cycle. This is kind of like a Moran process. We're going to pick an individual here, and we're going to kill him. Okay? And then what we're going to do is with probability m, replace that individual with one member of the meta community at random. Right? So the rate of coming from here will be proportional to the species abundance in the meta community. Okay? And with a probability of 1 minus m, what we're going to do is we're going to replace that individual with another individual in the island. Okay? Now, the math is kind of, it gets hairy and complicated, but the basic notion is really quite simple. Okay? You have a meta-community distribution, which is going to end up being the so-called Fisher log series in this model. This describes the species abundance on the meta-community. But then on the island, we're just going to assume that there's birth, death that occurs over here at some rate. But we don't even have to hardly even think about that, because we just run, from the standpoint of, say, a simulation, or we just run multiple cycles of this, where we have j individuals. And we always have j individuals, because it's like the Moran process. At every time point, we kill one individual, and we replace it with somebody either from the same community or from the island. Okay? Now, and you can imagine that in the limit of m going to 0, what's going to happen on the island? Yeah, so you'll end up with just one species, just because this is just random genetic drift. It's ecological drift, where one species will take over. Whereas if m is large, then it somehow it's more of a reflection of the meta community. Okay. Right. Are there any questions about what this model is looking like for now?
We talked about the Fisher log series.
Yeah.
Say we put it on the same axes as the.
Yes, this is a very, very good question. Yeah, so we'll do this in just a moment, because this is very important. Right, but I want to say just a couple things about this model. Right, so when I read this paper, what I imagined is that it really looked like this. That this was Panama, and that 30 kilometers off the coast, there was this island, BCI, Barro, Colorado Island. But that's not maybe an accurate description of what the real system looks like. Does anybody know where BCI is? Yeah, so it is in Panama, but it's not off the coast of Panama. I guess that was my original. Yeah, it's in the canal, right? So it's an island that was created when they made the Panama Canal. Okay, so this thing was not always an island. It's been an island for 100 years, right? And it's in the middle of the canal, right? I mean, they actually have cougars that swim back and forth from the mainland. So, it does make, but it does make you wonder of whether this is. I mean, it's just that it's much more strongly coupled to the mainland than I imagined when I read this paper at first. Okay, I don't know what that means for all of this, but. Certainly, what you expect this to be a more or less appropriate model depending on this. Because, of course, if you went and you sampled 50 hectares here, you wouldn't believe that it should have the same distribution. You'd believe it should be more like the Fisher log series. And then and there's some evidence that the things are tilted in the way that you would expect. And we'll talk about that. But it's tricky. And then, of course, you have to decide, and all this stuff, what do you mean by free parameters? And actually, it seems like people can't count. We'll talk about this in a moment, too. But yeah, because, of course, constructing the model, there's some sense of free parameters that you have there, right? Because we could have said, it's just going to be the Fisher log series. Or we could have said, it's going to be an island. Or we could have said, there's another island out here. And then that would be another distribution, right? And not all these things introduce more free parameters necessarily, because you could say, this is the same migration rate. Or I don't know, you could do something, right? But they are going to lead to different distributions, and you have that freedom, and you're trying to explain the data. So it gets into a lot of there are a lot of judgment calls in this business, right? All right. Okay, but let's talk about the Fisher log series, because this is relevant. So the model is very similar to what we did for the master equation in the context of gene expression. and the number of mRNA, right? So was the equilibrium or steady state distribution of mRNA in a cell, was that a Fisher log series? There, yes or no? All right, 5 seconds. Was the mRNA steady state probability distribution, was it a Fisher log series? Ready? 3, 2, 1. No. What was it? It's a Poisson, right? And you guys should review what all these distributions are, when you get them, and so forth. So what was the difference? Why is it that we have some probability P0, P1, P2, right? This could be mRNA, or it could be number of individuals in some species, with some birth and death rates. What was the key difference between the mRNA model, which led to this distribution becoming Poisson, and the model that we just studied here, where it became a Fisher log series? And I should maybe, I'll write down what the Fisher log series is. So this is the expected number of species with n individuals on the meta community. It was the Fisher log species. There was some theta x to the n divided by n. Yeah, what's the key difference? Yeah.
I think that the birth and death rates are both proportional to how many of the given individual there is.
Right, the birth and death rates are both proportional. Exactly. Right. In the Fisher log series, right? So what we have is that B0, and what should we call B0 in this model? Well, right now we're thinking about the meta community yet. Right. Speciation. B0 is speciation, which we're going to assume is going to be constant. All right, in this model, do we have speciation on the island? No. Right, the assumption is that the island is small enough that the rate of speciation is just negligible. Right, so speciation plays a role in forming the meta community distribution, but it doesn't play a role on the island in the model. Right? So this is speciation. But then what we assume is that B1 here is equal to some fundamental rate B times n, but it's B times, in this case, 1. Right? So more broadly, Bn is equal to some birth rate times n. Right? This is saying that the individuals can give birth to other individuals. Right? Now, we're not assuming anything about sexual reproduction necessarily or not. We're just saying that the kind of rates are proportional to the numbers. Right? So if you have twice as many individuals, the birth rate will be twice as large. Okay, this is reasonable. And similarly, all right, so this is P. This is Pn, and this is Pn plus 1, right? All right, so this is d of n plus 1 is equal to some death rate times n plus 1. All right, so each individual just has some rate of dying. It's exponentially distributed. This, again, makes sense. Right? Key difference is, what was the key difference between our mRNA model from before that gave the Poisson and this model that gives the Fisher log series?
Well, so with the mRNA, it's with that standard chemical equation where there's some fixed external input, but then the degradation is proportional to the amount that you have. So death is proportional and birth is not.
Perfect. Yeah. So in both cases, the death rate is proportional to the number of either mRNA or individuals, right? However, in the mRNA model, what we assume is there's some just constant rate of transcription. So constant rate per unit time of making more mRNA. So just because there's more mRNA doesn't mean that you're going to get more mRNA, right? But here we assume that the birth rate is proportional to the number. Okay? So that's what leads to the difference. Right, so this is one of the few other cases that you can simply solve the master equation and get an equilibrium distribution. And it's the same thing that we do from just always, right? Where we say, OK, you just at steady state, the probability, the fluxes or whatever are equal. And so you get that, P1 should be equal to P0. And then we have a B0 divided by D1. And more broadly, we end up getting, we just cycle through that the probability of being in the nth state, it's going to be some P0. And then we have to basically, it's going to be B0 divided by D1, B1 divided by D2, D2, D3, up to Bn minus 1 Dn. And indeed, if we just plug in what these things are equal to, we end up getting, there's a p to the 0, the fundamental birth over death to the nth power, and then we just are left with a 1 over n. Because we're going to have a 2 here and a 2 here, and those cancel, a 3 here and a 3 here, and those cancel. We're just left with the n at the end, finally. Okay. So this is, so this x over there is then in this model the ratio of the birth and death rates. Okay. So which one is larger? Is it A/1? Is it B is greater than D, or is it B/2 that B is less than D? All right. Think about this for 5 seconds. Do you think that birth rates should be larger than death rates, or death rates should be larger than birth rates, or do they have to be equal? Okay, ready? 3, 2, 1. All right, so we got a number of, all right, so we have some, all right, it's kind of distributed 1 and 2s. All right, let's go ahead and, well, it's maybe not that deep, not deep enough. Can somebody say why their neighbor thinks it's one or the other? Yeah, people are actually turning to their neighbor and thinking, yeah, maybe a justification for one or the other.
Yeah, so if this parameter b over d is greater than 1, then this distribution just is not normalized.
Right. So if b over d is greater than 1, so if x is greater than 1, then this distribution blows up. Right? Then it gets more and more likely to have all these larger numbers, right? OK, but then if b is less than d, shouldn't everybody be extinct? No. And the answer, can somebody else say why it is that it's OK for b to be less than d? I mean, if birth rates are less than death rates, shouldn't everyone be extinct? Because there's a rate b naught, exactly. So there's a finite rate of speciation. So it's true that every species will go extinct. Okay, but because we have a constant influx of new species, we end up with this distribution. That's this Fisher log series. Okay. Now, if you plot the Fisher log series, it looks a bit like this. Okay. But let's think about it a little bit. Does the Fisher log series, does it fall off A, faster or slower than this? Okay, Fisher falls, okay, A faster, okay, this is in this direction, or B slower. Then the island distribution. Okay, because you can see that this falls off pretty rapidly. Okay, ready? Maybe? 3, 2, 1. All right, I want everybody. Okay, okay. So there are a fair number of people that don't want to make a guess. Okay, it's going to be faster. Can somebody say why? Yeah. Is it going to be because of the 1 over n? I mean, the 1 over n is certainly relevant. Of course, the other, without the 1 over n, then we just have sort of a geometric series. And the log normal is not just a geometric series either.
This became faster than exponential.
Yeah, so this.
Whereas this has a very long scale. So.
That's right. So this falls off. Yeah, this would be kind of exponentially, and this is faster than exponentially. Right? And indeed, this makes sense based on the model, because this community, the reason that it has some very, very abundant species is partly because it gets migration from the abundant species here. Okay. Right, so this falls off pretty quickly. Right? But those frequent species still can play a pretty important role in the island community because the migration rate is influenced by this large numbers. And the other thing is, of course, that the rare species are going to often go extinct. So there's some. I mean, the distribution on the island is some complicated process of the dynamics to go on here plus sampling from here. But there's a sense that it's biased towards. It's not just a reflection of the meta community because it's biased the migration rate is sampled towards the abundant species. So the migration of these species ends up playing a major role in pushing the distribution to the right. Okay, so you have much more frequent, abundant species on the island as compared to the mainland. Okay. Yeah. Well, I'm sure they have on this one. I mean, there have been many. And I'd say that I think the statement that there's a faster fall off on mainlands than on the islands, I think, is borne out by the data. But I don't know if trees on the Panama side of the canal are actually better described by a Fisher log series as compared to this, though.
I guess my question was, like, the abundant species that we see on the island, like, is it just the result of diffusive drift, or
Well,
really?
I mean, the thing is that this also has the diffusive drift, right?
But is your sense that what really pushes,
Well, I think that you need both, the diffusive drift and the migration. But I think that the fact that the migration is from the mainland and it's biased towards those abundant things, I think is necessary or important. Yeah.
I guess just in terms of distinguishing between the niche and the neutral model, so as applied to the mainland, does the niche model predict also a log normal? Because it seemed like from the discussion earlier, the niche model also predicted log normal regardless.
Yeah, that's a good question. I think that. Yeah, in this whole area, I mean, it's a little bit empirical, and the niche. I mean, the fact that the niche model kind of predicts this, like this broken stick thing, predicts a log normal, right? And that they didn't say anything about islands there, right? I mean, I guess I think Fisher's original log series, he used it to describe. I think that was maybe the beetles on the Thames, but his original data set where where the Fisher log series was supposed to describe it. As it was sampled better and better, it eventually started looking more and more like a log normal anyways. Because it's hard to get the sample. I mean, it's easy to see the frequent species because you see them, right? But this tail can actually be very hard to see, right? Because you have to find the individuals, right? Yeah, so I think it's a good question of to what degree each of the models really predicts one thing on one place and another. And the thing is that there's always the tweaks of each model that adjust things. So I think it's a bit muddy. All right, but the one thing that I want to highlight so there was a lot of debates then between these different models, and each of the models have some fit. They have red and black. Kind of, there's one that kind of goes like this, and another one that kind of goes like that, and they're not labeled because they look the same. And you can argue about chi-squareds and everything, but I think it's irrelevant. They both fit the data fine. And the other thing, I mean, just the sampling of kind of like root end sampling. If you expect to see 10 species, then if you go and you actually do sampling, you expect to have kind of a root n on each one. So, I mean, the error bars I think around this are consistent with both models. So I'd say that the exercise of trying to distinguish those models based on fit to such a data set, I think is hopeless from the beginning. Okay. And then you can talk about the number of parameters, right? And if you read these two papers, they both say that they have fewer number of free parameters, right? And it's hard to believe that there can be a disagreement about this, but it comes, but then it's like, oh well, what do you call a free parameter? And then. Like what they say, any given RSA data set contains information about the local community size J. Okay? So they say, given that, it's not a free parameter because it's that you put that in. That's the number of individuals, and then out comes your distribution, right? And you say, okay, well, all right, that's fine if you don't want to call that a free parameter. But then when you fit the log normal to this distribution, the overall amplitude is also to give you the number of individuals in the meta-community, right? So if you don't call J a free parameter in this model, then you can't call the amplitude a free parameter when you fit the log normal, at least in my opinion. right? Yeah, so I think that they both have 3, right? Because if you fit a log normal to this, you have the overall amplitude. That's the number of individuals. And then you have the mean, and then the standard deviation or whatever, right? So from that standpoint, I think they're the same. Okay, yeah.
But I mean, when you fit the log normal, you don't impose. Do they impose the amplitude on the log normal?
Well,
I mean, it's still a parameter.
Well, the normal, yeah, no, that's what I'm saying. It's a parameter, right? I mean, the normalized log normal, you integrate and goes to 1, but then you have some measured number of individuals in your sample, and then you have to multiply by that to give you, right?
But like, is that what they do when they do their fit? Or
Yeah.
They keep that amplitude as also a parameter to.
Right. I think that you can argue about whether this is a free parameter or not, but I think that you can just put it as the number of individuals. And it's not going to affect anything, right? You could actually have it be a fit, a free. This gets into this question about what constitutes a free parameter or not, and and actually there is some subtlety to this, but I think at the end of the day, if you fit the log normal, the log normal is not going to look like this. You have to, you basically put in the number of individuals that you measured, right?
Does anyone calculate the negative log marginal likelihood?
Yeah, they've huge numbers of pages have been written about comparing these things. I think at some point it comes down to this philosophical question about what you think constitutes a null model, and this gets to be much more subtle. And I think different reasonable people can disagree about whether the null model that you need to reject should be this neutral model, or if it should be a niche-based model, or maybe it's just that there's some multiplicative type process that's going on and gives you distributions that look like this, and you need other kinds of information to try to distinguish those things. And in particular, I would say that it's really the dynamic information in which these models have strikingly different predictions, and then you can reject neutral type models, right? Because the neutral models predict that these species that are abundant are just transiently abundant, and they should go away, right? Whereas the niche-based models would say, oh, they're really fixed. And indeed, in many cases, the abundant species kind of stick around longer than you would expect from a neutral model. So of course, the neutral model is not true, okay? In the sense that different individuals are different. But it's important to highlight that even such a minimal model can give you striking patterns that are similar to what you observe in nature. All right, so I think we're out of time. So with that, I think we'll quit. But it's been a pleasure having you guys for the semester. And if you have any questions about any systems biology things in the future, please email me. I'm happy to meet up. All right, good luck on the final.